Hello and welcome. This is the pre-lecture video for the second half of Chapter 10. So let's begin with the kinetic molecular theory of gases. This theory basically helps us explain why ideal gases behave the way they do, and maybe helps us try to understand why why some gases start to break down in the ideal gas law as they begin to behave like real gases. So this will help us understand the whys behind some of the ideas behind ideal gases and real gases. And so one of the main ideas here is we have non-interacting particles that are flying around a container with a variety of velocities. These molecules can collide together, they can exchange energy, like a fast molecule can bump into a slow one, and then the resulting collision could cause the slow molecule to travel faster and the faster molecule to travel slower. So we should see things like the conservation of energy, where we're not creating energy through these collisions, we're merely just changing energy between a molecule and perhaps another molecule, or a molecule colliding with the wall of the container. So let's take a look at some of the tenets of the kinetic molecular theory of gases. Gases consist of large numbers of molecules that are in continuous random motion. So the molecules are all just bumping into each other as they collide with each other in the walls of the container. The combined volume of all the molecules in the gas is negligible relative to the total volume which the gas is contained. So it just means that the molecules are a lot smaller than the container that they're occupying, and they don't occupy a negligible portion of the container. Now we also were talking about earlier in the first half video for chapter 10 that as the pressure of a gas increases, then this assumption or this idea will start to break down. So as the pressure goes up, the amount of space being occupied by the actual matter of the gas is starting to increase, and then this approximation will start to break down. Attractive and repulsive forces between gas particles are negligible, so the particles aren't really inherently repelling each other like you might expect for two cations or two anions, but at the same time they're not quite attracted together either. So the particles should bounce off each other, but they shouldn't stick together for any periods of time during their collisions. So we can have collisions between molecules, but generally these would not be reactive collisions. They wouldn't cause reactions to take place, and they generally won't cause intermolecular forces to take place, at least within the approximation or the ideas of ideally behaving gases. So then energy can be transferred between molecules during collisions, but the average kinetic energy of the molecules does not change with time. So what this means is we might have some fast-moving molecules become slow-moving molecules through collisions, and vice versa, though overall the average kinetic energy of the molecules, the kinetic energy we could think of as the 1/2 mv squared, that this quantity here for all the particles will remain constant for the entire mixture. So the collisions can occur, but the average kinetic energy of the molecules does not change over time. Now, if the temperature changes, then that would break down. If we change the temperature of a gas, what's going to happen is we'll have more kinetic energy for the molecules to distribute through their motions. So that'll lead the molecules to having a higher velocity as a result if the temperature is increased. In fact, temperature itself is an idea or a measure of the kinetic energy of the particles. So the average kinetic energy of the molecules is proportional to the average temperature. So if you increase the temperature, you increase the kinetic energy of the particles, you therefore increase the velocity of those particles, as of course the mass of the particles would be not affected by the increase in kinetic energy. So change the energy, you make the particles move at a faster velocity as a result. So we can describe or compare how molecules travel. If we look at the speeds of a gas mixer, we actually have a wide range of velocities from relatively slow particles to relatively fast particles. And then we have a majority of the molecules, though, somewhere in the middle. So we're comparing, on the first case here, we're comparing a gas at 0 degrees C versus a gas at 100 degrees C. And on average, we have more fast-moving particles for the higher temperature gas sample. The average velocity of the particles is increasing. And also, we have a few different quantities for which we might define. We have things like the most probable velocity. The most probable velocity is the speed exhibited by the largest number of molecules. That's the sort of peak height, the velocity at the maximum point on the graph. We also notice perhaps that this isn't a perfect parabola. So this not being a perfect parabola means we're going to have more molecules traveling faster, and then we'll have less molecules traveling slower. And so the actual average velocity will be greater than the most probable peak. So the average velocity is the mean speed of all the molecules. And then there's a velocity that we call the root mean square velocity, the V, or the URMS, is the speed of the molecules which kinetic energy equal the average or the mean kinetic energy of the molecules. So we have the most probable, this is the highest point of the peak. The average is the midway point, so this is the average speed, the speed at which half the molecules are traveling faster, half the molecules are traveling slower. And then the root mean square velocity is the velocity that's associated with the average kinetic energy. So the average kinetic energy is defined by the temperature. And so these three quantities, two of them take on values that have a relationship to the ideal gas constant. The root mean square average is equal to 3RT divided by the molar mass. And we'll look at the second one that we can calculate off a similar equation later. So the root mean square velocity be 3 times R times T divided by the molar mass. We'll have to take careful consideration, though, of the units to see what units we get out for the velocity. So at any given temperature, the average kinetic energy of the molecules is the same. What that means is if we compare O2, N2, water, helium, and neon, hydrogen, that when we compare these different gases, that on average, all these gases at the same temperature have the same kinetic energy. So if they have the same kinetic energy, then that means the lighter particles have the higher velocity, the heavier particles have the slower velocity, since all these particles have the same energy. So it's like if the simple analogy would be that if you have a heavy individual and a light individual, usually the light individual can travel at a faster speed or a faster velocity. So the root mean square velocity we can calculate by taking 3 times R times the temperature divided by the molar mass. Okay, so we can calculate the root mean square velocity, we can plug in molar masses, and we can see that if you plug in a larger molar mass, that should result in a slower velocity at a given temperature. Now the units here of this problem will work out like this. If we want to get out a root mean square velocity in units of the SI units of speed, meters per second, we probably want to plug in the SI units for molar mass and for the ideal gas constant. So what does that mean in terms of units? Well, let's imagine we're trying to calculate the root mean square velocity. Let's just pick a gas. Let's say for helium, we're trying to calculate this for helium at 25 degrees C. Okay, so we'd plug in that for the root mean square velocity. Let me move this over just a little bit. So we're going to take the root mean square velocity as 3 times 8.314 joules per mole Kelvin times 298 Kelvin to get the temperature to cancel out. And then we're going to divide by the molar mass, 0.00400 kilograms per mole. Now, why did I go kilograms per mole here? Well, it has to do with the 8.314 joules per mole Kelvin. 1 joule is a kilogram meter squared per second squared. Okay, so I want the kilogram to cancel, and then if I leave the meter squared per second squared underneath the square root sign, then take the square root, then the unit works out to be meters per second. And so probably not so surprising, if we want to get a velocity out in units of SI units, then plug in the ideal gas constant in SI units. The SI unit quantity would be 8.314 joules per mole Kelvin, and a joule is a kilogram meter squared per second squared, hence we want to plug the molar mass in the units of kilogram. So we just use the other unit of R that we had defined earlier in the first half video when we were looking at the ideal gas constant. So we can look at effusion and diffusion. Effusion is the escape of a gas through a tiny hole. So you can think of a gas where we have a relatively high pressure, we have a pinhole, a little tiny hole that gases can escape from, and then we have a much lower pressure on the opposite side, so you can think of like a balloon or a tire, or something where we have a high pressure on one side and a low pressure on the other. And so effusion is the escape of gas molecules through a tiny hole. So the gas molecules in the top half effuse through this pinhole when they happen to hit the pinhole. So the particles are traveling around, and any of the particles that hits the pinhole can be ejected or lost through the pinhole. And so the gas that has the highest velocity will escape more quickly because it's going to have a higher probability of striking the pinhole. So a lighter gas will be traveling around faster and have a greater probability of escaping through the pinhole. So if we had two different gases, if we had, say, argon and helium, so imagine some of these particles are argon, some of them are helium. Helium travels faster, argon travels slower. We're going to get more helium escaping out from the pinhole when we first pop that pinhole. So we can actually purify gases this way. You can actually imagine having a series of pinholes, and then you can keep purifying out a gas. If you control or relatively slowly allow the gas to effuse through the pinhole. Now, diffusion is the spread of one substance through a second substance. You can imagine the smell of coffee reaching one end of the house if you're brewing a pot of coffee. And so the coffee molecules obviously are gaseous. And so you could imagine if you could control the vapor pressure in your house or the atmospheric pressure in your house, that if you could reduce the atmospheric pressure, you could do that if you moved. So like, let's say you go up in the mountains. So if you go up in the mountains, you'd probably find if you're cooking, the smell would make it to the other end of the house much more quickly because the molecules could travel through the medium much more quickly because they're not bumping into as many air molecules. So you can imagine that maybe for your coffee smell to go from one end to the other, maybe it bumps into a particle, goes this way, bumps into another air particle, goes this way, and starts bouncing all the way around before it makes it to the other end of the house. So the more air molecules in a room, the higher the atmospheric pressure, and then the longer it's going to take a substance to diffuse. Also, you could look at a lighter particle going to travel faster and hence diffuse more quickly. So diffusion, a lighter particle travels more quickly, and then also reducing the surrounding pressure will allow the substance to diffuse more quickly. So real gases are the description of the behavior of real molecules in the real world. So the ideal gas equation starts to break down at high pressure and low temperature. So the ideal gas law works pretty well, though, at high temperatures and low pressures. Well, why is that? Well, at high temperature, we don't have the involvement of intermolecular forces as likely because the particles would be traveling around with a great enough kinetic energy to break those attractions. So at high temperatures, the likeliness of two particles sticking together is that likeliness is lower. If you lower the temperature, the liquid or the gas particles will eventually drop out and form a liquid phase. And so at some point you're going to have a gas that's being described as droplets or particles containing more than one molecule traveling together and changing what we believe to be the number of actual moles. So the particles, once they start to interact at a low temperature, would become problematic with the ideal gas equation. Also, at high pressure, we have some problems with the ideal gas equation due to the actual quantity of the container being occupied by matter. And so we get actually opposing behaviors that at the low temperature limit, we break the ideal gas law due to, if we think of calculating a pressure, due to nRT over V in the ideal gas law. If our apparent number of moles is truly smaller, then the real pressure should actually drop compared to what the ideal gas law is predicting. And then likewise, if our container volume at a high pressure should be smaller because it really should be the free space volume that we plug in, not just the container volume. If we could plug in the free space volume is going to be smaller than the volume of the container. So the real volume we're supposed to be plugging in is smaller than what we're actually plugging in. And so then that's going to make the real pressure become a higher quantity. So we get higher pressures at the high pressure limit than what we would even predict with the ideal gas law. So the ideal gas law is under predicting pressures at the high pressure limit, and then at the low temperature limit, it's going to be doing the opposite. It's going to be calculating a pressure that's too high. Now, I don't necessarily expect you to work through with sophistication the thought here, but just seeing that there's two different types of issues here: the low temperature limit, where particles sticking together affects the moles, and the high pressure limit, where we're impacting the volume. So our deviations from ideal gas behavior, if we go to a high pressure, then obviously the percent of space occupied by matter is increasing. And then if particles are sticking together and forming droplets, or we have intermolecular forces causing the particles to stick together, then we also have a problem with the ideal gas law. So we can correct for this behavior. So we can do that through an equation known as the van der Waals equation. So this tries to account for the fact that molecules can attract together and also could repel each other. And then also it tries to correct for the volume occupied by the actual matter itself. So taking a look at the van der Waals equation, it looks like PV equals nRT, like the ideal gas equation. but we just have a correction for the intermolecular forces. It's really correcting for the intermolecular forces that are being lost due to attraction and adding them back into the equation, and then subtracting away the container volume to really account for free space. We're trying to plug in free space here to calculate the volume of the actual container. So N times B works out to be roughly the size or the space that's being occupied by matter. So let's take a look at A and let's take a look at B. So let's actually look at B first. B is in this column here. So some B values are shown. And so the B value relates to the space that a molecule is occupying or an atom is occupying. So if we have more of the compound, if we have more moles, then it's obviously going to be occupying more space. Units here, liters per mole. Volume per mole multiplied by moles tells you the volume that the matter is occupying. And let's just look at relatively a couple examples here, like CH4 to CCl4. Obviously, CCl4 is bigger. Chlorine is a lot bigger than hydrogen. And so, so the CCl4 takes up more space. It has a larger B value. So B is proportional related to the size of the molecule. So B is directly proportional to the molecular or the atomic size, or just size overall. And so generally you find a larger molecule takes up more space and has a larger B value. Then likewise, A is related to the strengths of intermolecular attraction. IMF stands for intermolecular forces of attraction. And so the value of A, none of these are negative, so none of these molecules are repelling each other. These molecules are all attractive to each other. And the value A is increasing as the substances grow larger. For substances that are similar, so if you compare the noble gases, A goes up, if you will, linearly. If you look at some like H2 to N2, that it gets bigger for H2 to N2 because nitrogen's a bigger molecule. N's bigger than H. If you compare the CH4 to CCl4, being bigger is better in terms of intermolecular forces when we're comparing similarly structured molecules. If we also look at something like water has a relatively high A value, so substances that are polar or strongly polar have a relatively larger A value as well. So A would be proportional to molecular polarity and also molecular size for similarly shaped molecules. We'll see in chapter 11 that our strengths of attraction for nonpolar compounds goes with size. So like bigger nonpolar molecules or atoms become more attracted together the larger they are. So this helps explain why, for example, the melting points and boiling points down the halogen group increase. Same thing with the noble gas group. It's because you're moving to a larger atom. Larger atoms stick together better. They have more affinity for each other due to their increase in size. And we'll see a picture for that a bit more in detail when we get to chapter 11 a little bit later. So for something we might do here in chapter 10 would be comparing the ideal gas volume and the van der Waals pressure that we might calculate. For a gas, we could compare half a mole of N2 in a liter container at 25 degrees C with 7.5 moles of N2 in the same container. So this quantity here is probably going to have a bigger issue with the V minus NB term because our gas should be occupying a pretty big portion of the container. We might pull out our A and B values for N2 so that we can use them here from the previous slide. So the A value is 1.39, and that's liters squared ATM per mole squared. And then the B value is 0.0391 liters per mole. Okay, so let's do the ideal gas law first. That's easy. So the pressure will be equal to nRT divided by V. And so I'm just going to plug in the moles. That's half a mole, 0.5, divided by 0.08206, or excuse me, the moles, 0.5 moles times 0.08206 times the temperature, 298 Kelvin, and divide by the volume, a liter, gives us a pressure of 12.2 atmospheres. And so then we can calculate the pressure using the van der Waals equation. So we have the pressure plus n squared A divided by the V squared and then V minus NB, so that equals nRT. So I'm going to divide by that V minus NB here, start with that right off the bat, and I'm going to subtract the N squared A divided by V squared. And so then, and that gets rid of this over here. So my van der Waals pressure will be equal to nRT divided by V minus NB, and then minus N squared A times V squared. So now this term here is the intermolecular force term, and this term here is a correction due to the size. Okay, so let me actually do the N squared A divided by V squared calculation real quick. So that would be 1.39 liter squared ATM divided by mole squared. So I'm multiplying by moles, that gets rid of the mole squared. So I'm doing, so this would be equal to this minus, so 0.500 moles squared times the A value divided by the container volume of a liter squared. So liter squared in the denominator cancels here, mole squared cancels here, so we get just ATM out from this calculation. So go 1.39 times 0.5 squared divided by a liter squared, so that's 0.3475. So there's a, in terms of the 12.2 ATM total pressure here, we had maybe an error of 0.3 ATM due to the intermolecular force term. And so then let's look at this V minus NB. So we have a liter container minus 0.5 moles times 0.0391. So the V minus the NB, so I'm plugging in container volume of a liter minus half a mole times B. So that works out to be 0.980 liters. So the volume was only off by 0.002 liters. So not a big error introduced by assuming the container volume was our free space volume. And we'll divide this into the nRT value, so 0.5 times 0.08206 times 298. So that's 12.2. And so ATM times liters, so the volume cancels, so this gives me just ATMs when I do this arithmetic here. So I divide this by 0.980, so that works out to be 12.5. And so that volume ends up being a little higher. Once I get rid of the volume that was occupied by the matter, it has a slight increase in the pressure, and then we lose some of that pressure due to the intermolecular attraction. So I subtract the 0.3475 from this, and I get 12.1. So the container volume increases the pressure that we would expect, and then the intermolecular forces decreases the pressure that we would expect. So the real pressure here, pretty close though. So relatively still low in terms of pressure, and we're still getting a pretty good approximation with the ideal gas law. So if we move to a higher pressure, say we put more nitrogen gas into the container, then likely we'll see a bigger breakdown. So let's calculate our pressure with the ideal gas law again, nRT divided by V. Only difference here is I'm using 7.5 moles times 0.08206 times, so 7.5 times 0.08206 times 298 divided by the same 1 liter container. This is 183 ATM, and I plug in the numbers above, and so my pressure from the van der Waals equation, a better approximation of the real pressure, 7.5 times 0.08206 times 298, and then divide by the quantity V minus NB, where it's a liter minus 7.5 moles times 0.0391. Okay, so that gives me right off the bat, if I plug in this whole term here, the nRT divided by V minus NB works out to be 259.5 ATM, and then minus the N squared A divided by V squared. And so this is still the free volume, so I'm still plugging in the 1.0 liters here, still plugging in the 7.5 moles here, so I'll go 7.5 squared times the A value, 1.39, and then dividing that by the liter squared gives me this value here to be 78.2 ATM. So when I do this arithmetic, 259.5 minus 78.2, 181.3. So still not bad. I mean, so I'm not getting a bad agreement even at this relatively high pressure here. And so if I do this, I might just want to look at this quantity here for one more second. Take 1 liter minus 7.5 times 0.0391. That's now a volume of 0.707 liters. And so if we keep putting more gas in, we're going to make this quantity here even higher. And then this term here likely at some point is not going to make up for it. We're going to see this pressure start to go higher. So like if we were to do this again, if we say put 15 moles of N2 in. So if I did 15 moles, and I work out the ideal gas law, pressure, so 15 times 0.08206 times 298 gives me a pressure of 367 ATM. And if I work in the van der Waals equation for a better approximation of the pressure of that container, so I do 15 times 0.08206 times 298, then I divide by quantity 1 minus 15 times 0.0391. That's over 800 ATM, and then I subtract 15 squared times 1.39 for the A value, divide by a liter squared, gives me a pressure of 574 ATM. So if you keep changing the pressure, if you increase the pressure more and more, then the V minus NB term kicks in, and it's a much bigger criteria in increasing the pressure from where the ideal gas law would be predicting. So when we're under predicting the pressure, that means that the second term is having a bigger impact. This N squared A divided by V squared is having a bigger impact at reducing the pressure due to intermolecular attraction. And then if we see that the pressure, that the van der Waals equation, the slightly better approximation of the real pressure, if we see that's going higher than the ideal gas law, then we know that that's primarily a result of the space of the container problem kicking in and being the bigger error being introduced at the high pressure limit. Okay, so a few different scenarios for breaking down the ideal gas versus the real gas. Real gases are better described by the van der Waals equation because it's accounting for intermolecular attraction and molecular size. All right, so that's all for this video for the introduction to the second half of Chapter 10. Thanks for your attention. Look forward to seeing you in class.